start with Ruff, an extremely fast Python linter and code formatter written in Rust, presented by Charlie Marsh.
Hi. Okay, my name's Charlie. I work at a company called Astral. We build high-performance developer tools for the Python ecosystem. And we're most well known for Ruff, which is what I'm going to be talking about today. Ruff is an extremely fast Python linter written in Rust. And the thing I want to focus on today is this part. So what makes Ruff so fast, which is a question I get very often. The sort of title slide says, Ruff is a linter, but Ruff I think is actually kind of more than a linter, and our vision for it has kind of grown and continues to grow over time. So we view Ruff as a complete static, or we want Ruff to grow into a complete static analysis toolchain for Python. So Ruff is a linter, which means it can identify problems that you might have in your Python source code, things like unused imports, or maybe you're using deprecated APIs. If you've used tools in the past like Flake8 or Pylint, Ruff can do similar things to those tools. Ruff is also a code formatter. So if you've used tools like Black in the past, Ruff can auto-format your Python source code to adhere to a consistent style. And it's also a code transformation tool. So in addition to identifying problems like unused imports or deprecated APIs, Ruff can actually fix a lot of those problems for you automatically. So if you've used tools like isort or PyUpgrade in the past that do automatic code transformation, Ruff can do a lot of that stuff too. Most people interact with Ruff over the command line interface, which looks something like this. We look at your source code, we give you diagnostics, we tell you, hey, this import's unused, we give you some nudges around how to fix it, and then Ruff can fix problems for you automatically. So here, Ruff is removing some unused imports, it's rewriting some type annotations, it's changing the quote style to be slightly more consistent. So I started working on Ruff, I think a little under 2 years ago. And since then, it's grown quite a bit. So we're now at, I think, a little over 18 million downloads per month. We have about 500,000 installs on our VS Code extension, something like 27,000 stars, and over 400 contributors. And thinking less quantitatively, a little bit more qualitatively, Ruff has now been adopted by a lot of the big and very mature projects in the Python ecosystem in open source, like FastAPI, Pandas, SciPy, and also by a lot of the companies that are using Python at significant scale. And the reason I bring this up is because I think at this point, it's nice to be able to talk about Ruff in the sense that it's not some experimental thing. It's very well proven. It's been used across a lot of projects over a pretty long, a longer period of time than a year ago. So Ruff does a lot, and it does it at this big scale, and it does it very, very quickly. So this is a benchmark of running Ruff over the CPython code base itself. And so even on very large code bases, Ruff can complete in milliseconds. It could be 10, 100, even 1,000 times faster than other tools you might be using. And it's fun for me to be here now and to show that graph on stage because I came to PyCon last year, and it was my first PyCon, and I didn't really know anyone. And I was sitting in the audience, and Al Swigert gave a talk about the Python code tool landscape. And halfway through the talk, he put this slide up there and was like, you can just use Ruff. It's this great thing. It can do all this stuff. So for me, being here, it's very cool to be on stage now and to get a chance to talk about this a year later when hopefully we've made Ruff a lot better, but also just feeling a lot of gratitude to have the opportunity to talk about it here. So for this presentation, I want to talk about what makes Ruff so fast. And I think in order to talk about that, we first need to briefly talk about how Ruff works. So what is Ruff doing when you actually run Ruff check or Ruff format? I sometimes view Ruff as a compiler, which is maybe a little bit of an unorthodox thing to say, but it's a compiler that takes in source code and it produces diagnostics. And diagnostics is just sort of a fancy and a little bit more of a general term for lint errors. So Ruff is a tool that takes in Python source code and it produces lint errors. And so like other compilers, we can kind of view, we can break Ruff's operating model down into a pipeline, a series of steps where each step is kind of feeding into the next. And the first step there is tokenization, or you sometimes see this referred to as Lexing. So, imagine that we've discovered all your Python files, and like we have some Python source code, like y equals x plus 12. And we need to get to a representation that we can actually start to analyze and understand. Like we need to do some analysis of that source code. But when it comes in, it's just like a string, right? It's just like a string that says like y equals x plus 12. And that string isn't really amenable to program analysis. It's hard. We can't really like make sense of it as a raw string. And so a lot of what we're going to be doing is kind of mapping to higher and higher level representations of the code. And the first step there is this tokenization step, where we basically go through and we try to understand what are the individual pieces here, ignoring like the raw text. What are the different tokens that comprise the program? So we might say, okay, we have a name token, which refers to a y, or the name itself is y. Then we have like an equal sign, then we have another name token, then we have a plus sign, and then these two characters at the end comprise a single token, which is an integer token with the value 12. So, we start with just the raw string, and we map to, we tokenize it out into this token stream, which is just a slightly higher level representation of the program. It's something that we can it starts to capture some of the meanings of the language beyond just being raw text of y equals x plus 12. Once we have the token stream, we move on to parsing. And parsing is doing a lot of what we would do naturally as programmers to try and better represent the actual structure of the program and what it's doing. So here, like we as programmers might look at this and say, okay, we have an assignment operator. On the left there's a y, and on the right there's this x plus 12. So parsing takes that token stream and breaks it down into this representation of the program. And we can take that sort of one step further and say, on the right we have this x plus 12. Okay, that's actually a binary operator with an x on the left and a 12 on the right. We fill in the leaf nodes, and this gives us an abstract syntax tree. So you might be familiar with this, but if you think about this representation versus what we started with, which was just that string of y equals x plus 12, this actually captures like the structure of, or some of the structure of what the program is doing, right? It's an assignment of a variable on the left, and on the right there's an addition operator. And this is something that we can actually start to make sense of, which moves us on to semantic analysis. So in semantic analysis, imagine that we have this y equals x plus 12 example again, and maybe we add a print y afterwards. Semantic analysis is about starting to understand the relationships between different parts of the programs and starting to ascribe some actual meaning to the different symbols that we're seeing. So, in this case, through semantic analysis, we'd want to be able to understand and ask and answer questions like, okay, this y in print y is actually the same y as the y that we assigned to on the previous line. Similarly, this print here, like that isn't defined anywhere in the file, right? Like I'm not actually, if this is the whole file, I'm not actually defining print anywhere. That's a Python built-in. And so in semantic analysis, we'd want to be able to identify, hey, this is actually the print built-in, and it's okay that it's not defined in the file because we know it resolves to something that Python has built into the language. So this whole process of building up a data structure that lets us ask and answer these kinds of questions, we refer to as semantic analysis, and the output here is Ruff's semantic model. So this is the thing that we use throughout diagnostic analysis, which is the process of taking that understanding and creating diagnostics or lint violations. So in diagnostic analysis, we're kind of tying everything together to give the user feedback about problems in their program. So if we think back to this example, maybe we have a lint rule that says, oh, actually, like we don't want to ship print statements to production. Like we should be using the logging APIs or something else. In this case, the diagnostic analysis is kind of taking everything together, right? We started with the string of like y equals x plus 12. We broke it down into tokens. We started to understand that, okay, the print statement is a function call. The semantic analysis then helped us understand that that function print is a built-in, and then the diagnostic analysis encodes the actual rules. So, okay, we shouldn't be calling the print built-in in our production code. We might then also offer an auto fix. So maybe the fix in this case is just, we're actually just going to offer to remove the print statement, and the user can accept or reject that suggestion. So, a slightly different way to view this process is, what are the outputs of each step? And the first step, again, produces that token stream, takes in source code, produces the token stream. The second step takes the token stream, produces a syntax tree. The third step takes the syntax tree, produces a semantic model. And then the fourth step takes the semantic model and generates a bunch of diagnostics on your code. And each of these steps feed into one another. Okay, so that's like the briefest possible overview I think I could give into what Ruff has to do when it tries to analyze your source code. So now I want to focus on what actually makes Ruff fast. And I'm going to talk through a couple of what I view as like core principles, or the things I think about when I try to explain why Ruff is fast, and then go through a series of very specific examples of things we've done in Ruff that I think illustrate some of these ideas. So, the first thing that people will say, and the first thing I will say, is Rust. And Rust is a big part of what makes Ruff fast. Ruff is written in pure Rust. It's about 300,000 lines of Rust. Ruff doesn't actually depend on Python at all. You don't need to have Python installed to use Ruff. You also don't need to have Rust installed. But the thing about Rust is like Ruff has gotten significantly faster over time. So I guess keen eyes at the beginning, I showed the benchmark and the benchmark from last year. Like between those two benchmarks, Ruff got about twice as fast. Like we sped it up by about, it's about twice as fast now as it was a year ago. And like both of those versions of Ruff, right, were written in Rust. So it's not just Rust that makes Ruff fast. There's thankfully a lot more to it. And the way that I kind of view the role of Rust here is that Rust gives us a really fast baseline. Like the baseline performance of the program is very good. But the more interesting thing for me is that Rust gives you a lot of the tools you need to write really fast programs. So, the ceiling in terms of the kinds of things we can do in Rust versus in some other programming languages is very different in terms of how much we can optimize and how much we can do beyond the kind of the baseline initial implementation that we had. And, I think part of this is that Rust kind of forces you to care about a lot of the details that matter when you're trying to write very high performance code. So for example, like memory usage, like when you're writing Python, it's very intentional. It's an intentional goal and strength of the language that you don't actually have to think about how you're using memory. Like you just kind of allocate things, you just kind of like create variables, and then those variables are allocating memory somewhere, and that just gets managed for you. Like those variables get cleaned up at some point by the garbage collector, and you as the programmer very rarely have to think about where you're using memory in Python and like when that's going to be cleaned up and all those kinds of things. And that's like a strength of the language, but allocating memory comparatively is very expensive. And so having very fine-grained control over how we allocate memory, like where we allocate memory, whether it goes on the stack or the heap, ends up being really important for writing software that goes from being written in Rust and fast to being written in Rust and like very fast. So, I think Rust is a big part of the story behind why Ruff is fast, but I don't think it tells the whole story. And I think it's some of the things that we're doing with Rust that are a lot more interesting and that also can apply to writing code in other programming languages. Okay, so second thing that I think about when I think about like why is Ruff fast is there's kind of like some fundamental deduplication that's happening when you run Ruff as compared to other solutions. So if you think about like, imagine you have a setup where you're running like PyFlakes, PyCodeStyle, PyDocStyle. Like these are three different static analysis tools. They all look at slightly different things. Like PyFlakes is mostly looking at like program correctness, things like unused imports. PyCodeStyle is mostly like a PEP 8 compliance rule, so it's looking at code style. And PyDocStyle is looking at do your doc strings adhere to, do you have all the information in them that you want? Do they follow the standards? So if you run like each of these three tools on your code, each tool will have to go through that process of tokenizing the source code. So that first step that we went through of like, now you have a raw string, you have like all this source code as a raw string, you now need to break it down into tokens. Like each of those tools has to do that independently. And then each tool comes up with its own sort of intermediate representations to create diagnostics. So like PyFlakes will actually create an AST, PyCode style and PyDoc style do slightly different things, but each of those tools is doing a lot of work. And in Ruff, we just tokenize once, parse once, and analyze the source code once. And all of the rules that we implement operate off of the same intermediate representations. So there's like some fundamental deduplication that we've been able to achieve by building, kind of bundling more behavior together and creating this common infrastructure for all the different diagnostics that we support. So next thing I think about when I think about what makes Ruff fast is trying to do more work at the same time. So broadly, like concurrency and parallelism, and viewing that as something that we want to maximize as much as we can. Rust is a big part here. Rust has this idea of like fearless concurrency, where most concurrency bugs ideally are actually compiler errors. So like the compiler should not let you write a lot of concurrency bugs. And we take strong advantage of that. So Ruff has a very simple data model. If you think about like the pipeline that we went through on those previous slides, we can do that for every file in parallel effectively. So for every file independently, we can be like tokenizing, parsing, generating the semantic model. But you can also think in maybe a slightly more unorthodox way about like data parallelism. So SIMD is this idea of, it stands for single instruction, multiple data. And it's the idea that you can have CPU instructions that can run in parallel across many pieces of data at once. It's a slightly different way of thinking about concurrency and parallelism. But if you're thinking in this mindset of like, how can I do as much work as possible at the same time? So we'll sometimes look at operations, like maybe in that tokenization step, and say, okay, this is expensive. We're like searching for something in a really big string. Can we speed that up with SIMD? So thinking in terms of how can I leverage concurrency and parallelism as much as possible, both at the macro level in terms of the architecture, and then at the micro level in terms of individual operations that we're doing, is a big part of, I think, how we get the performance that we get. And then, lastly, and I think most importantly, there's no like one thing that makes Ruff have the performance characteristics that it does. I think like the only way that you achieve and maintain high performance over time, the way that you like expand scope in your program while making it faster, is you really have to have a culture that treats that as a first-class principle, a first-class citizen. So for us, a couple of things that I think about when I think about performance, and that I've tried to instill in the project. One, performance is everyone's problem. So it's not that like every part of Ruff has to be extremely micro-optimized, but I do think everyone has to care. So thinking about performance should come up in code reviews, in design documents, in the initial architecture for how you're building something out. You want to be thinking in terms of I have a bunch of considerations, and performance is an important one of them, not just shipping as quickly as possible or shipping something that kind of works. Second, small wins can really add up. Sometimes performance is like some huge rewrite that you do that like makes everything twice as fast. Sometimes it's like 10 changes that make the program 1% as fast. And similarly, you can ship like 10 regressions that each regress performance by 1 or 2%, and your program is just getting slower and slower over time. So it's not necessarily about like micro optimizing everything you do, but I do think at times it's easy to dismiss a consistent 1 or 2% improvements that you're shipping consistently. And so I think some of the examples that we'll walk through will follow that philosophy. Another thing I try to do is like I really encourage people in the project to kind of follow their curiosity. And what this means in practice is like sometimes it's worth thinking about how to optimize something, how to make something faster, even when it's not the most important thing to be doing. And even when the thing you're looking at isn't the bottleneck in the program as a whole. Because like worst case scenario, often you build some intuition, you probably have fun, and I think that's good. And ultimately, you learn a lot. So, a big part of Ruff's story over the past year has been bringing other people into the project who know a lot more than me about how to write fast software. Like, I didn't know anything, a year or two ago about like SIMD, or like if you're familiar with terms like alignment or like cache lines. Like, this was all very new to me. And so, like, I kind of view Ruff today as like a lot faster and a lot more well optimized than it was a year or 2 years ago. But I'm also trying to be aware that like there's a lot of stuff we're not doing, and like it could be faster and faster still. And that's just part of the process of like being a programmer and learning a new skill set. So I think it's easy to like look at a lot of these things, and the quote, the premature optimization is the root of all evil quote obviously comes to mind. And I think that quote is like, I think that has been taken a little too far in some contexts, because people sometimes take it to mean, you shouldn't really care at all about performance. I think would be like the most egregious way to interpret that. But like, I think for me, it's not about premature optimization. It's about like making sure that the decisions that you make are grounded in data. So like if you're looking at something small, like maybe it's only 1% of the program runtime, but like ideally that started in a trace, or it started in somewhere that it was brought to you and you noticed it. It's not a function that you picked out blindly and you have no idea how much time it's taking up. Similarly, when you go and implement an optimization, like putting up a PR and just being like, yeah, this is like a more optimal way to do it, is not really a useful exercise. Like everything that we ship gets benchmarked a lot. So, for me, it is often worth working on things that are just small parts of the program, but everything you do should be grounded in data. And that comes from both how you choose what to work on and the solutions that you ultimately end up shipping. Like performance work can look like a lot of things. Sometimes it's getting like a big architecture right. Sometimes it's something small like finding one function on a hot path and optimizing it. But like neither of those things can really happen, I think, if you don't treat performance, if performance is considered a non-goal in the project. All right. So given those core concepts, I want to walk through a couple examples that I picked out of things we've done in Ruff over the past year or two. And these won't always be like the biggest optimizations that we've ever done, but I do think they're useful because they illustrate some of these principles. So I want to start by talking about integer parsing. So in Python, you can have like, let's say like arbitrary length integers roughly. You can have just like really, really big integer constants, and the language will just deal with it. And if you only, if you mostly write Python, this might seem really obvious to you, or you might be saying, of course you can do that. Rust is a little bit different. Rust, like some other languages, has integer types at fixed sizes. So you can have like a U16, which is an unsigned 16-bit integer. It's an integer that can take on values between 0 and 65,535. You can also have like a U64, an unsigned 64-bit integer that can take on larger and larger values, but takes up more space in memory. So if you think about what we're doing, like in Ruff, we need to be able to parse Python source code and then represent it in Rust. So what happens when we see like a huge Python constant? Like imagine that we have a Python constant that's bigger than the biggest thing we can store in a U64. Like we need to represent it in Rust somehow. So Python is going to throw us like really big integers, and we need to figure out a representation, a way to model that in Rust, which models integers very differently. And so, the way that we did this initially, and this isn't, you see this in other languages too, we used what you would refer to maybe as like a big integer class. And the idea here is that instead of storing that number we parse as like a single U16 or a U64, you can think of it as storing like a series of digits in a vector or in a list. So that number at the top, maybe we'd store that as a list that's like 1, 8, 4, 4, 6. That's not like, you can do it more efficiently than that, but the core idea is that instead of storing it as like a single integer, you model the data in terms of storing all the digits, and then you write operations in terms of how do you combine the digits. This is a very convenient representation because we can represent really, really big integers, but it's also very inefficient. And the reason for this comes down to thinking about the stack and the heap. And if you're not familiar with these terms, that's totally fine. The stack and the heap are two different places that you can allocate and use memory in the program. And the way that I like to think about it is that the stack is typically intended for data, objects, and such that have a fixed size. So like, if you think of a U16 or a U64, like a U16, okay, that's a 16-bit integer. It's something that has a fixed size. We can allocate that on the stack. The heap is where you allocate things that have variable or sort of unbounded size. So something like a list or a vector or a string even, things that can kind of grow and that you might not know the size of ahead of time, those will typically be allocated on the heap. Allocating on the heap is like way more expensive, and so in general, in a very simplistic sense, like we would much prefer to be allocating on the stack versus the heap, especially for things that we're going to do often or constantly. So in this case, a U16 and a U64, those are things we can allocate on the stack, which would be great, but we're now using this big integer representation that uses a vector. So for every integer that we parse, we're now doing a heap allocation, because we need to go create a vector to store all the digits. The thing is, like, in the real world, most integers, like most integer constants that you see in Python are very small. Like, when's the last time that you wrote Python code that had like an absolutely enormous integer constant? Like, you may have done it before, but the vast majority of integer constants that you see in Python code are like 0, 1, 2, 3, 10, right? And these are really small numbers. These are numbers that we can fit in, even in like a U16. So the thing that we did is very simple, is we implemented this sort of small integer optimization. So the idea here is that if the integer that we're parsing is small, we just store it in a U64, which is very cheap. And then if we happen to encounter a very large integer that's too big to fit in that representation, then we use that big integer class, or that big integer representation. So for the vast majority of integers, we can now avoid a heap allocation. And this is like actually something that we did. The representation in the PR is like slightly different. And it sped up the Lexer or the tokenizer by somewhere between like 2 and 8%, all through avoiding those allocations. And so, a couple of things I think about here. One, like, optimizations don't exist in a vacuum or in isolation. They exist in the context of your data. So if most Python integers were like really big, this would not be a very useful optimization, because almost all the time we would still be going down that vector path. But like, most Python integers are not big, and we can leverage that fact to try and come up with a more optimal representation. The other is, this is an area where I think it's useful in Rust to be able to think about like stack and heap allocations, and think about, have control over like how we're representing those things. And then thirdly, like, you can see here the tooling is really important. We use this tool called CodSpeed. It gives us like continuous benchmarking every time we put up a PR, so we see things that got faster, things that got slower. So again, like, the decisions we make need to be grounded in data. Having great tooling is a big part of that. All right, here's a totally different example. So in Ruff, we support what we call suppression comments. So you might have an import that's marked as unused, and then you can put a comment on the end of it. We follow like Flake8's convention here, where you can put like comment, no QA, and then the error code that you want to ignore. And the way that we originally implemented this is we used a regular expression. It looked something like this. Regular expressions are amazing. We use them. The person who wrote the Rust regular expression crate works on our team. But they're very powerful and flexible, and they can also be kind of like harder to optimize. Because if you think about what the regular expression engine is doing, like sometimes you see these really wild regular expressions. It has to be able to take those and map those down into logic about how it's searching through strings, how it's identifying things that match. Maybe it needs to support, finding groups in the match. That's like a really, really complicated set of operations. And it can be hard sometimes for regular expression engines to optimize these kinds of things the same way that you could if you knew exactly what you were trying to do. So one day I saw this show up in a profile, and I decided to try. Actually, I tried like a bunch of different things, but the core idea was that I wrote this out more like a kind of a traditional Lexer. And it sounds like, I think, fancier than it is. The basic idea is I just wrote a function that took that string, the comment, and it said like, okay, consume the hash character, and then consume any white space. Then consume, the exact string, NOQA. Okay, then consume the colon, blah, blah, blah. And like, if at any point you see something you don't expect, you kind of just eject. It's very, very, very simple. And this, like writing it out by hand like this, sped up the parsing of those comments by like somewhere between 3 and 10 times, depending on the contents of the comments. And so Ruff itself got like 1% to 2% faster, right? It's like pretty small. And so you have to ask, like, does this even matter? And the answer is like maybe not, right? It really depends. Like a regular expression might be totally fine for something that runs once or runs infrequently. It might also be totally fine if like your program isn't hyper-focused on performance, or if you're writing like a one-off script or something that you're going to throw away. It's probably like very much the right choice to use a regular expression. But for Ruff, which is going to run like, I don't know, hopefully like hundreds of millions of times a month or something and analyze like billions of comments, like I think it does matter. Like being able to get a 1% to 2% win on something as small as this, I think is awesome. And if you think this is ridiculous, good, because like it is kind of ridiculous, and we do this kind of ridiculous thing everywhere. The thing I would maybe go one step further even, which is to say like, even if this didn't end up leading to a measurable speed up in Ruff, I still think it was worth the time that I spent on it, because I actually learned a lot about text parsing and like how to write really optimal text routines. So again, this is something that we actually did. I benchmarked like 10 different implementations, and then we shipped it. And this is just the kind of thing, this for me was like a follow your curiosity thing, where I was like, I want to try it, I think I'm going to learn a lot, and then we ended up getting a nice performance improvement. All right, slightly different example, and I really struggled to explain this one in the dry run, so I'm a little nervous about it, but hopefully people will understand it. So there are really two ways to think about like the location of a token or like a piece of code within a program. So like we as humans would look at this and we would say, okay, that import OS, that's on like line 2. It's at the start of line 2. And the OS token in particular, we might say like, oh, that's line 2, column 8. And if we as Ruff were to like report that back to the user, we would want to tell them, hey, it's like line 2, column 8. But for the machine, like for the program, that's actually like really not a useful or convenient representation. Because if you think about like what the machine sees when we give it this source code, it's just like a big string, right, with like a bunch of new line characters in it at different points. And so, the program would think about that OS token as being at like, let's say character number 22. So we have these two different ways of thinking about the location of that token. And one is like really optimized for humans. Like if I told you have an unused import at character number 22, I think you'd be like really frustrated. So we have this one representation that's really good for humans and one that's much better for machines. Okay, so in Ruff, we really had two things that we would typically do with this kind of, like, why do we need to do this, right? The first is reporting diagnostics back to the user. So if we want to say like the import is unused, we want to tell them where it is, and we want to tell them based on row and column. The second is that often we just need to like slice into parts of the program to look at the raw source code and maybe extract it. We do this like constantly. For example, maybe in that fetch function at the bottom, maybe we need to know whether there's like a trailing comma at the end of the last argument. That's not something that's going to be covered by the abstract syntax tree, which just represents like the semantic arguments. But for the Ruff formatter, for example, we need to know that because it affects how the code gets formatted. So the way that we might do that is we would kind of like say, hey, can you give me the exact source code, the exact text that corresponds to this part of the program? So we're doing that like all the time. So initially in Ruff, we indexed everything in the program, like every node and every token, by row and column, which in hindsight, I feel like I've grown a lot in the past like year or two because like I'm really embarrassed by that. But that's sort of the point of the example, I think. So we indexed everything by row and column. And again, that's a representation that's really optimized for humans and for reporting. But like reporting is something we do really infrequently. Like reporting errors back to the user, comparatively, we only do that at like the very end of the program. And most files don't even have any errors. Like most of the time when you run Ruff, most files don't have any errors. Like if you think about running Ruff on average in the world. So we were optimizing for something that we did very infrequently, as opposed to something that we did very, very frequently. So if you think about, okay, I need to know whether the fetch function has like a trailing comma at the end of the arguments. If all you know is that that function starts at like line 13, if that's what I tell the program, then to get to that, it has to traverse over the source code. It has to actually look for all the new lines. It has to go count first new line, second new line, third. It's very, very inefficient compared to just saying, hey, it starts at character number, I don't know what the character is, character number 120, and then it can just, just very simply take a substring. So this is something that we changed. We started indexing everything in the program by byte offset. So it's everything in Ruff, the abstract syntax tree, everything is indexed by the sort of byte offset, the character offset effectively in the program. And then we translate at reporting time back to row and column. So we pay later to translate to row and column instead of paying up front and using row and column everywhere. Again, this is something that we actually did. I didn't do it, but we did it as a team. And it was a really big change. It was like 6,000, 7,000 lines. And the formats here have changed a lot over time, sorry. But the sort of like summary is that it made Ruff as a whole about 10% faster. And it also mitigated about a 50% regression that we were seeing in like a new feature that we were building. So it was like huge performance change. And all we did was change effectively the internal representation to better match our own data access patterns. All right, one more example. And this one's different because it was actually like a really, really big change. But in Ruff, we have a parser, the thing that takes Python source code and turns it into the abstract syntax tree. And our parser used to look something like this. So this actually is not Rust. This is, it's sort of like Rust. It's a custom language that was used by this parser generator that we used. And the idea behind the parser generator is you kind of write out your code in terms of this language, which is like almost Rust, but a little bit simpler. You're kind of writing out patterns. And then the parser generator reads this and generates the Rust code for you. So the parser, in the end, our parser code was generated. We would write out this grammar, and it would spit out like tons and tons of Rust code to parse Python source code. Our new parser looks more like this. The details are not super important, but it's a little bit more, I would say, like manual. We're kind of writing out, hey, when we want to parse a global statement in Python, we start by looking for the global token. If we see that, then we're going to look for a comma-separated list of identifiers like global x, y, z. And if that works, then it's like a global node. So we kind of went from something that was, I would say like a little bit more declarative to something that's more imperative. We were kind of writing out the grammar before and the parser was generated. Now we're writing out the parser like entirely by hand. All right, so why do we do this? So first, there are a couple of reasons. The first is that we want to be able to represent and parse invalid programs. So like Ruff is something that lives in your editor. And when you're in your editor and you're like typing, you have syntax errors all the time, right? Like you type def space and like you're about to type a function name and now you have a syntax error. Right now, like today, when you do that with Ruff, all your diagnostics like disappear until you type the function name and keep going. And we want to get to a point that we can actually like parse the program up to that error and give you diagnostics based on the program. So making it robust to people who are using Ruff in an editor. This was really hard to do with the parser generator because it didn't really support it and we didn't really have control over it. Whereas with this handwritten parser, we have like total control over error recovery and everything. Two, it got really hard to maintain the parser generator, especially because Python's grammar has become a lot more flexible in the past few releases. So for us, the parser generator, in order to be able to do this amazing thing where you like define the grammar and it automatically generates the code for you, which is amazing, it has to put limitations on the kinds of things it can support. And some of the things that Python started to do, that parser generator couldn't really support it well. So we were more and more writing our own clever tricks around the parser generator to get it to work with new Python grammar. Whereas with the new parser, we have like total control over it. And then the third thing, right, which is the point of this talk, is that we saw like a huge performance boost. And not only that, it kind of opened the door to doing a lot more optimization in the future, because generated code was very hard for us to optimize. Like it gets generated, we don't really have any control over what code gets generated. We can't add our own custom handling for important or special paths. Whereas now, it opens up like a huge room for optimizing things in the parser and the Lexer because we have full control over it end to end. So the reason I want to talk about this is because I think performance, it doesn't always have to be a trade-off. I think a lot of the times when people think about optimizing and writing performant code, they think about layering on tricks or fast paths or hacks or things that make it harder to maintain a program over time. But here with this project, we actually had a bunch of additional goals. It wasn't just about performance. We ended up with an implementation that we are way more happy with. It achieves a lot more of our goals, and it also happens to be significantly faster. But the other thing is you kind of have to pick your battles. Not every project should choose to write their own Python parser from scratch. But it makes sense for us because for us, we're going to invest a lot in this. This is a core piece of infrastructure. Everything we build will benefit from having a better parser. And it was just squarely in our critical path of something we always knew we wanted to do. So picking where we choose to make these kinds of investments, very, very important. Again, this is something that we did. Once again, I didn't even work on this at all. It was a 100,000 line of code change. And the parser itself got a little over 2 times faster. And Ruff as a whole got 20 to 40% faster. So again, the performance was an amazing improvement. Both these programs were written in Rust, right? But there's a lot that you can do even within the confines of these things are written in a certain programming language. All right, so a couple things that I think about here. Rust enables us to build very different kinds of programs. The ceiling in terms of how fast we can make things, Rust unlocks a very interesting design space there. But a lot of the things that I've talked about in this talk around building fast programs, I really think can apply anywhere. Thinking about having great tooling, so having continuous benchmarking, getting good at profiling, having a culture where performance is a first-class concern, thinking in terms of the data that your program's operating on. Some optimizations make sense and some don't, depending on what typical workloads look like. None of those things are specific to Rust. Those things also apply to Python. They apply to whatever programming language you're using. Sometimes performance does not matter. Sometimes you're working in contexts where this actually doesn't need to be a goal. And yet I still think sometimes it is worth caring about and working on performance even when it doesn't matter because it feeds into some of these other things. In the worst case scenarios, you kind of learn something interesting and something new. And all this stuff is very learnable. Like I said, this was all very new to me, a year and a half, 2 years ago. And over the course of that period of time, everything I've talked about today, basically, I learned or happened in the past year or two. So, writing, thinking about performance, working on performance software, it's a whole set of skills, and it's not something that's totally inaccessible to people. If you enjoyed this, I collated a huge set of other things that we did in Ruff, other optimizations, and the slides are available on my GitHub. These all link to pull requests, so depending on how much Rust you like, there's a lot of interesting stuff in here. And I think that's it. I don't know. Do we have any time? No.
If anyone has a question, can go to the mic, and we can extend a bit.
Hi. I have a quick one, if possible. Do you have any fun examples about an optimization that wasn't worth it?
Decisions that weren't worth it?
That wasn't worth it.
That were not worth it? Yeah, I do actually. So like in in Rust, you can do this kind of interesting thing where you can tell the compiler that if you panic, like if you hit a certain type of error, you actually just want like the whole program to crash, and you don't want to give a stack trace or any. You don't want to have any handling for that. You don't want to give useful information back to the user. This is an option that you can set when you compile your program, and it makes your program like actually a lot faster, because if the program doesn't have to worry about giving you like a stack trace or useful information when it crashes, there's a bunch of stuff it doesn't have to track, like a lot of debugging information, other things on the stack that it no longer has to track. So I set that option at some point early in Ruff's development because it made Ruff like 15 or 20, like 15% faster maybe. And I was like, oh, this is cool. But the problem is then when we have like actual programming errors and Ruff itself crashes, like users don't get any useful feedback. And in particular, like if we were analyzing like 100 files, if we crashed in any one of them, we wouldn't be able to give diagnostics for all the rest. So like the user experience got a lot worse even though Ruff got faster. And then someone else on the team smartly came in and reverted that change. And it made Ruff, I mean, it does mean that at some point in time, maybe we can speed up Ruff another like 15% just by turning that back on when we're more stable. But that was something where like, I think I made the wrong trade-off in terms of benefit, choosing performance over user experience.
Hi, I'm sorry.
Hi.
I'm very new to Rust. I started looking at Udemy and like doing Rustlings as far as learning Rust. So I'm very curious about like your research on like the tooling and optimization and profiling tools. Like how are you selecting those tools for your optimization and things like that?
Yeah. So there's a couple things. One, I like look at other projects that I respect and I see what they're doing. And so that's a very good way, I think, and other people who are like working on this kind of thing. Like if I see they screenshotted something or they had a PR where they added some optimization, like there's just a lot of learning from other projects in open source. And then there's an interesting book called just like an online. It's more of a website, I guess, than a book called, what is it? The Rust Performance Book by Nicholas Nethercote, which is a very useful introduction and accessible introduction to a lot of interesting ideas, like thinking about how do I, like it's sort of like what are the things that you should care about and what are some of the like, it's sort of like a set of tools and ways to think about optimizing your Rust program.
Hi.
Hi.
Thanks for your talk. I was wondering, you talked a bit about trade-offs between performance and user experience. I want to ask you about trade-offs between performance and general maintainability, because it seems that you're doing stuff that maybe makes things harder to maintain. Where do you draw lines there, and how do you go about thinking about that?
Yeah, totally. I mean, I think maybe we're too early in the life of the project for me to give definitive answers on how to think about that, because we may come someday to regret some of the things that we've done. But one thing I think about is that part of it comes down to being very data-driven. Like sometimes people will make changes that they think are like, in theory, like more optimized or like do better. But if we can't measure it in benchmarking or in a profile, then like I typically say we shouldn't do it. So like having some guardrails around where do you draw the line, like what you asked is like, does it show up in data? And like, can you prove that the thing you're doing is actually like important? That's at least one thing I think about.
Hi. So I think your example regarding changing the representation for integer constant values is really a good example of optimizing code. But then what's the specific reason for Ruff to actually memorize the specific values of those integers instead of just indicate that this is a constant of type integer? Is it going to do some checkings that is about the specific values?
Yeah, we actually do like have some rules that rely on looking at the actual values. So for example, like one example is if you do like sys.version info checks that compare against a constant. So if it's a common pattern where people will do like if sys.version info is greater than like 3.3, 9, we do need there to be able to compare to like the constant integer values. One thing that we noticed in that process though is if the value is large, we never actually, like we only ever compare, sorry, what's the right way to say it? We only actually care about values when they are one of a small set of values. Like there's no value greater than like, I don't know, like 13, for example, that we would ever actually care about. So in practice, we don't actually parse integers that are larger than a U64. We just store a reference to the string. So we actually don't even analyze them when they're very big because we've figured out that we only care about the integers when they happen to fit into that size.
Okay, thank you very much.
Yeah.
Hi.
Hi.
So you can correct me if I'm wrong here, but it sounds like Ruff actually comes pretty close to compiling Python to Rust. Is that something that it's looking to do in the future? And if so, how close is it?
I would say no, it's not something we're looking to do in the future, and we're probably pretty far away from it. So Ruff originally used a parser from a project called Rust Python, which is like it's a little bit closer to what you're describing. It's a Python interpreter and runtime written in Rust. So you're still writing Python code, but it executes it in a Rust, like you have a Rust runtime that's kind of executing it. But we've actually made a lot of changes, moving away from that direction. We're more and more building tools that are focused on static analysis rather than running code. And so some of the things that we've changed over time have actually brought us further from that. So it's a little bit different, but Rust Python might be interesting to you if you're curious about that.
Cool. Thank you so much.
Yeah, of course.
Hey, Charlie, thanks for the talk. I have a question about what is called plugins in the Flake8 world. So if there is a custom rule set that I want to implement, is there a use case where I can make a separate repo, define that rule set in Rust, sort of equivalently to how Flake8 plugins work, and then I sort of pip install it to the project to do rough check, and it includes this rule set with the speed advantage of the main Rust project?
Yeah, so we don't support that today. We don't have, Ruff is not extensible in any way, so it's a limitation of Ruff as compared to Flake8 and other tools where you can actually write your own extensions and load them. It's probably one of the biggest feature requests we've had for a long time. It is harder to do in Rust. I think the design space of ways that you could accomplish it is actually pretty interesting, and I think it's something we'll do eventually, but we don't support it today.
Okay, thanks.
No problem.
Hi, great presentation. Ruff is an awesome tool. I had two questions. So obviously making a parser is a huge feat, a huge amount of work. And one of the things, or two of the things I'm curious about is what was your approach to, towards this problem? And secondly, have you seen any interesting other open source projects that have kind of extended off of the parser or Lexer in Ruff?
Yeah, so interestingly, the parser itself, it all started from a contributor who was, they were a student and they were writing a Python parser as part of their, for a school project, basically. And they built it and they got it to the point that it was worked enough that they could benchmark it. And they showed us hey, it's actually a lot faster than the current Ruff parser. Would you be interested in this? And we kind of went through this evolution where we were yes, but it kind of needs to pass, so the first bar was it needs to implement our AST, because there's a lot of decisions that you have to make when you think about how you want to represent the program. And then the second bar was we need to get it to the point that it can pass all of our tests. And then the gap from there to shipping in production was actually a lot of work because Ruff for us to switch a parser, it's just a really big change. And if we shipped a bunch of regressions, a lot of people would feel that pain. So we spent a lot of time fuzz testing the parser, and which is like running. You could think of it as like auto-generated code examples against it, some of which will be kind of pathological. We spend a lot of time on that, and we spend a lot of time running the parser over lots of real-world code and real-world projects. So the gap between like the parser, there were just like a series of milestones where it's like the parser exists, the parser adheres to our AST, it passes our test suite, it has been rigorously fuzz tested, it's been tested across a bunch of real-world code examples, and we actually we had like almost no, shockingly few errors in the parser when we shipped it. I think I didn't work on this at all, so I'm allowed to say it. Like, I think the people who worked on it did a really amazing job of like testing it very thoroughly. The project Deptree, I think, uses Ruff's parser now. So they just pull in the parser, but they haven't like extended it in different ways. There's another project in the JavaScript ecosystem called OXC, which is, I look at that project a lot when I think about how to do things like correctly and in a very fast way. So like we kind of try to take inspiration from other projects, but I don't know so far if we've influenced very many. Maybe it's too new. Thanks.
Thank you.
Yeah, so Ruff is an awesome project, and I see there's like lots of work invested in it to make it so fast, and yeah. So that just made me think, like, it seems like it's not just a bunch of people doing this in their free time. It seems like there's very capable people working full time on this. So yeah, my question is kind of, where is the money coming from that funds this, and what motivation is there to maybe get the money back? So,
Sure.
So like, yeah, I mean, yeah. So what are plans in the future? Like, I'm assuming like Ruff or you guys also now created UV. Like, I'm assuming they will stay free, but then what other things are on the roadmap, or what are ideas how you could kind of get funding back, or how will this be sustainable in the long term?
Sure. So so we're a venture-backed company. So the money that we spend right now to hire people and work on this stuff full time was raised from investors. Ruff and UV are free, open source, MIT licensed, and they will continue to be free, open source, MIT licensed. Our goal as a company is to build out tooling. Hopefully it's really good. Hopefully a lot of people want to use it, and then build and sell services that integrate well with it, that are kind of the natural next thing that people need when they're building software with Python. So that could be like a lot of different things. I don't want to like tease too many because it's hard for me to commit to, but you could kind of imagine it like, imagine you're using Astral's software for like linting, formatting, maybe like type checking, it's your package manager. There's a lot of things that you then do in the software development process that I think could be better integrated with that tooling, whether it's stuff in continuous integration or like even like code deployment. Again, I'm not saying we're necessarily going to do any of these things, but that's the core idea behind the company. Is we want to keep building out this open source, have an incentive structure where we're very much incentivized to like keep it open source, keep it truly open source, and grow it as much as we can, and then use that as a mechanism to get people to pay us for other software that integrates with it.
Cool. Thank you.
No problem.
So in the name of performance and optimization, have you, for any reason while developing Ruff, had to dip into the Necronomicon of Rust and use unsafe code blocks for any reason?
Yeah, pretty sparingly. We had no unsafe for a long time. Trying to think of some there are some people on my team who have like different opinions about this, and thankfully some people on the team who are like really try to avoid unsafe a lot. So I think we generally have a good culture of not using much unsafe. For example, there are things we could be doing like sometimes I see projects where they'll use unsafe and they'll disable bounds checking in a lot of places, and we don't do that. I think sometimes we do some memory transmuting stuff where we know it's safe, but it has to be wrapped in unsafe. So we generally try to do it sparingly, but we have, if you look for unsafe in the code base, I think you can probably find a couple examples. Yeah.
Got it. Thank you.
Yeah, thanks.
Thanks for the talk. The principle of making data-driven decisions from your benchmarks is sort of contingent on having good, sensible benchmarks.
Yeah.
So what is your strategy there? Because it all comes back to that.
Yeah, it's very hard. We generally have two kinds of benchmarks. We have some micro benchmarks, which are the ones that run on every PR, and those are we've taken some representative files and that's benchmark just the Lexer on these files, for example. And we've tried to make that more diverse over time. So I think we have some examples now that are largely Unicode characters, for example, because when you have programs that are not written, that are written using lots of different Unicode characters, there's lots of optimizations you can do if you assume ASCII, but if we make all those optimizations, sometimes it makes the Unicode representation slower. Anyway, so we've tried to make that more diverse over time. And then the other thing we do is we sometimes do whole program benchmarking, where I guess maybe a fancy way to say we actually just run Ruff as a whole on different projects and try to rigorously benchmark how much did Ruff as a whole change. So we try and do a mix of those two things, but it is very hard.
Okay, thank you.
Yeah, no worries. Okay, I think that's everything. Thank you. Thanks for all the great questions too. Appreciate it.